Hey ChemStars, this is Mrs. Vanderlei bringing you more ChemStar gas law video. We are now going to be talking about the combined gas law. This is much more realistic as pressure and volume and temperature are all going to change. So, and some of the problems that we had before is like we release a hot air balloon, all right? And what happens when the pressure goes down? The volume's going to go up. Well, temperature also changed. So how do I deal with something like that, okay? Well, let's kind of quickly review something. So here are the past videos. We already learned about Boyle's law, where it's a relationship between pressure and volume, but temperature was held constant. Here's Charles's law, where we have volume and temperature, but pressure was held constant. And there is a Gay-Lussac's law, where we had pressure and temperature, but volume was held constant. What happens if we don't hold anything constant? Well, what I want to show you, I want to go back to that FET lab again, and we're going to find out. All right, so I already put in, I don't know, I think 4 pumps of gas here. And so notice I'm not holding anything constant. In the last 3 videos, I could always hold something constant. So right now, my temperature is 300 Kelvin. My pressure is, I don't know, I want to call it 30-ish, upper 29s-ish. All right, I saw a 28 in there. All right, so somewhere in the 29 region, okay? So what can I change? I want to change volume, all right? All right, ooh, what's happening to pressure? Pressure is going down, we knew that, but I also want to change temperature, and now look at that, pressure is going back up. So you see how if I change 2 of the 3 variables, I really cannot predict what's going to happen to the third. It all depends. Now, if I go back to the original condition, all right, and let me put my 4 pumps in. All right, and let it, settle out again. So what happens if I open up the volume? Pressure goes down. But remember, I added heat, so pressure went up. And if I added enough heat, the overall pressure was going to increase. Remember that? So I can predict, though, if I increase the volume, we know pressure is going to go down. But what would I need to do for temperature to make the pressure go down? And that would be, oh, that's a direct relationship. I need to cool it. So notice as I cool it, pressure continues to go down. So there I can predict what's going to happen. All right, look how slow those molecules are moving. So if you have 2 conditions that lead to the same conclusion, then yeah, you can say, yeah, sure, pressure is going to go down. But if you have competing conditions, there's really no way you can tell, all right? You have to do the math. Oh, so let's go do the math. Good idea. So how do I determine, the math, all right? What's the math equation? Well, we're going to combine, hence the title, combined gas law. We're going to combine Charles and Boyle's and Gay-Lussac. So you notice that pressure and temperature are always pressure and volume are always on the top and temperature is always on the bottom. So that's what the combined gas law is, where pressure and volume are on the top and temperature are on the bottom. So you kind of combine all 3 laws to get this law. So let's see how the math works. So if a helium balloon is filled to a volume of 2.4 liters at 25 degrees Celsius and at 1.30 atmospheres. Aha! If the balloon is let go and goes up in the upper atmosphere, remember how we did that before and we didn't consider the change in temperature, but it gets really cold up there, all right, where the temperature is now negative 35 and the pressure is really low at 0.0100 atmospheres. What is the new volume, all right? So before, I didn't say anything, but I was rather concerned that, the volume of that balloon is like 400 and something back in the I think it was the Boyle's law that we did. That balloon would pop, all right? Would it truly pop? So let's see what happens here. Here's my combined gas law. So what is my P1? I think my P1 is what, 1.30? So 1.30 ATM. What is my volume? That's 2.4 liters, isn't it? All right, let me move this over. All right, oops, and I'll get rid of my V1. So what is my temperature? Well, it looks like it's 25, isn't it? All right, so let's see here. 25. Oops, silly me. 25. Hello. All right. Is that right? What do I always have to do with temperature? It is not right. What do I have to add? I have to always add 273 in order to get my Kelvin temperature, don't I? All right, so what's my P2? My P2 is 0.0100 ATM. And what's my T2? It's negative 35, isn't it? Mrs. Vanderwall, I know it is not. All right, it's not negative 35. What do I have to do? I have to add 273. Okay, so let's kind of talk about this first. What did my pressure do? My pressure went down. So what would volume by itself then do? Volume would go up. That's why we had like a 400-liter balloon that would probably pop, all right? But wait a minute, what did the temperature do? Temperature went down, so volume would go down based on temperature alone. So here you can't predict what is going to happen to volume, all right? Is it going to go up because of my pressure and pop? Is it going to decrease and deflate and quit flying? I don't know. Let's do the math, all right? So what I did here is I redid the problem, but this time I added my temperatures. All right, so here, whoops, here I have that. So now what? I need to do the math. So just like what we said before, we need to cross multiply and divide, all right? So I'm going to do this. So let me show you on the calculator what I'm going to do. So I'm going to take the part that is not where the volume is. So I'm going to multiply these two. So I'm going to take 1.30 times 2.4 times 238. All right, so I'm going to do these guys first. Here's my cross multiply. Now I'm going to divide by both these terms that are with the V. So divided by 298. All right, and then I'm going to divide by 0.0100. Oops. Well, let's see here. Can I delete that? Oh, poo. All right, so let's do this again. So there we go. Make that equals. There we go. Phew, figured it out. So my answer is 249.1812. So do you see what I did? I multiplied these numbers and I then divided by those numbers, okay? So I get 249 is my answer. All right, and so what did the volume do? Oops, what did the volume do? The volume went up, okay, from 2.4 liters to 249 liters, at least not 400. Now, I don't know what kind of material that balloon is made out of to know if it can expand to that extent. Hopefully so it doesn't pop, but it is what it is. So that's my answer, okay? So let's go on to number 2. All right, so if a gas is filled in an inverted graduate cylinder underwater and the volume is 9.3 at a temperature of 18.5 degrees Celsius at a pressure of 745 millimeters of mercury, what is the volume at STP? Uh-oh, what is STP? That, back in the day, I think it was back in the 80s, I think so, maybe the 90s, there was a group called the Stone Temple Pilots. Is that what I'm talking about? No, silly. STP is standard temperature and pressure. Let me write that down for you. All right, so standard STP is equal to standard temperature and pressure. So what is that equal to? 1 ATM, and everything that's equal to 1 ATM and 0 degrees Celsius, or 273. Okay, so you might want to jot that down. So if you ever hear of STP, don't think of that rock group like I do. All right, it's standard temperature and pressure, which is 1 atmosphere. All right, it's 1 atmosphere and 0 degrees Celsius. So here we go. Here we have our equation. Why would I do this? Because everything's changing. All right, my pressure changed from 745 millimeters of mercury to 1 ATM. My volume is going to change, that's what they're asking for, because the temperature also changed from 18 degrees to 0 degrees, all right? So let's check this out. All right, so my pressure is, what I just say it was, 745 millimeters of mercury. All right. And my volume was 9.3 mils. And I'll move that because that looks bad, right? All right, let me get rid of my V1 over here. And I probably would need a parenthesis over here. That's fine. All right, now what? What's my temperature? My temperature is 18.5 degrees Celsius. No, Mrs. Vandoy, you need to add 273. All right, I'll do that. Okay, now what? My P2 is, well, it's 1 atmosphere. But folks, this is not in atmospheres. Let's go back to the front page. Okay, I'm sorry, it's the second page. Okay, do you remember this? These are all equivalent to 1 ATMs. Why? Because all of this, if you need a little bit of a review, go back and watch that first video when I explained all of this, all right? But for what you need to know is that 1 ATM is equal to 1,300 pascals or 101.3 kilopascals, or 760 millimeters of mercury, or 760 torr, or 29.92. So I need to convert. I can't use ATM in the equation I gave you, but I can use this. That is ST, or SP, that's standard pressure. All right, it's 760 millimeters of mercury. So let's go back to the page we're working on. So I'm going to move this to be 760 millimeters of mercury times V2, and then my temperature is 0. Well, automatically I know that can't work. Why not? Because anything divided by 0 is infinite, undefined. All right, you can't. What is it? All right, so we have to add 273. Okay, and so now I'm ready to do my math. So I redid it, adding all my values together. I'll move it down a little bit. All right, so once again, what do I need to do? I need to cross multiply and divide, okay? I'll get out my calculator. There it is. Let's clear this puppy. All right, so now we have 745 times, where's my times button? Here it is, times 9.3. Now, does my volume have to be in liters? No, it does not. All right, milliliters is fine because my units are going to cancel out. Okay, I'll show you that in a minute. So 9.3 times 273. All right, what's that equal to? Big number. All right, so now let's divide it by 291.5. All right, and divide it by again 760. So my answer is 8.537, yada, yada, yada. So with 2 sig figs. Why 2 sig figs? Because the 9.3 is 2 sig figs, okay? And I want to show you something real quick. Let me show you these guys. Let's delete and delete. So look at my units, okay? Let's see here. Let's use red, okay? Notice that my millimeters of, whoa, don't want to do that. I don't know if it's going to be red again. No, yeah, okay. So my millimeters of mercury cancels out. My kelvins cancels out. And so now what is the only unit left? Milliliters. So that is the unit of my volume. Okay, hopefully that makes sense. So let's go ahead and do number 3. Okie dokies, if 9 liters of gas is at STP, so we start off at STP, the pressure is changed to 760 millimeters of mercury, and his new volume is 8.7 liters. So what's the final temperature? So why don't you pause this, figure it out, and come back when you're done. All right, welcome back. Well, hopefully you start off with this. Here is my standard pressure. Why did I use 760 millimeters of mercury? Because I looked over here and saw my new pressure is in millimeters of mercury. If they gave it to me, let's say in inches of mercury, I'd have used 29.92. If they gave it to me in kilopascals, I'd have used 101.3 kilopascals. So whatever unit your pressure is in is what, you put here, okay? And I start with 9 liters, and standard temperature is 0 Celsius, which is 273 Kelvin. So my new pressure, my new volume, all right? So let me get my calculator back. So this time, what do I need to do? Now let me put you down again. What am I going to do this time? I am going to cross multiply and divide. Okay, so why do I multiply this side first? Because the temperature, my unknown quantity, is not part of this. All right, so I multiply where my temperature is not. Let's put it that way. So I'm going to cross multiply here and divide. Okay, so let me get out my fancy dancy calculator. There we go. And so let's try this. Let's go with 273 times 700 times 8.7. All right, let's make that equal. Now what am I going to do? I'm going to divide this by 760. And then I'm going to divide it again by 9.0. All right, so I got 243. So I got temperature is equal, to 243. Okay. That's in Kelvin. Well, what's that in Celsius? All right, so subtract 273, and I got negative 30 degrees Celsius. All right, well, I have a guest speaker for you today.